All right, so let's start with a very last talk. So it's a special lecture by Ashoke Sen, Gravitational Waves from Soft Theorem.
Thank you very much. So I'd like to take this opportunity to thank Hisam and all the other organizers for organizing this amazing conference and for inviting us all here. So my talk today will be on gravitational waves from soft theorem. Okay. It will be somewhat different in spirit from the other talks in this conference. It will be a talk in classical gravity in 4 dimensions instead of quantum gravity in 11 dimensions. Okay. Nevertheless, we will see that somehow we arrived at these results by thinking about quantum gravity in higher dimensions. Okay. And I will try to explain this connection as I go along. So let us imagine that there is a violent explosion in space, okay, and some bound system just breaks apart into fragments, okay, and the fragments just fly off. So this process of course will emit gravitational waves, and if we have some detector D that is placed far away from the source, from the place of explosion, okay, it will eventually detect some gravitational wave, okay, and the wave front is measured by the difference between the metric and the flat metric eta mu nu. I am assuming that the space time is asymptotically flat. Okay. So the difference between the actual metric and the flat metric is what we call the gravitational wave signal. Okay. And the kind of processes that I have in mind here are, for example, explosion of supernova, okay, where a star explodes into fragments, okay, or we can have something like a binary black hole merger, okay, where a system of 2 black holes, which we think of as a one bound system, just explodes into one remnant black hole and a bunch of gravitational waves. We can also consider a more general situation, okay, where you have collision. Okay. So here what I have in mind is that we can have a set of objects which come together, okay, interact strongly, and then produces another set of objects. Okay. So set of objects come together and goes out as another set of objects. This process will also produce gravitational waves. Okay. And here a simple example is the bullet cluster. Okay. So this consists of a collision between 2 supercluster of galaxies. Okay. So it is not just 2 stars, but 2 supercluster of galaxies, they just pass through each other. Okay. So that you can think of as a collision, and this collision will produce gravitational waves. Now in general, if you want to compute the gravitational waveform h mu nu, which is the difference between the metric and the flat metric, that is produced during processes of this kind, it is complicated. It is complicated for several reasons, okay, and here are the 2 primary reasons. Okay. First of all, when the objects are close, okay, they may undergo complicated non-gravitational interactions, okay, for example in the explosion of supernova. Okay. The electromagnetic and nuclear forces play a big role in the kind of interactions that these objects have, okay, and that will certainly affect the gravitational waveform that is produced during this process. The second complication comes from the fact that the gravity is nonlinear. Okay. So even if you have a situation where the interactions are purely gravitational, okay, and here one example of such a process is black hole merger. Okay. Since black holes have no hair, okay, in the process of merger of 2 black holes, the only interaction that is relevant is gravitational interaction. Okay. But even in this case, actual computation of gravitational waveform that will be produced is very complicated because of the nonlinearity of gravity. Equations are nonlinear, and what one does normally is to use numerical methods to compute this, okay, or one uses some approximations in early time, okay, where one can do some calculations because gravity is weak in that regime. What we will try to argue in this talk is the soft graviton theorem actually can lead to some exact results for these processes, okay, and this will be the focus of this talk. Okay. Of course, we will not be able to get the full handle on this gravitational waveform, but some properties of the gravitational waveform can be extracted from soft graviton theorem, which as we will see is a property of quantum gravity amplitudes. So, here is a brief plan of the talk. Okay. So, I will try to spend much of the time giving a summary of the main results and the various aspects of these results. So, this will include both new viewpoint for older results, and the older result that I have in mind in particular is memory effect. I will explain what this corresponds to. And this connection was started by the work of Strominger, and then various other people have contributed to this aspect. And then we will also discuss some new results, which are not known before, but this also, as we will see, comes out of soft graviton theorem. So, after giving the summary of the results, I will give a classical derivation. This is a classical result, right? It is gravitational waveform produced during classical process. So, there has to be a classical derivation. So, I will give a classical derivation of these results, and then I will describe how this was derived from soft theorem. In fact, historically this came first, and then later on we gave a classical derivation, and we will see that by thinking of this from the perspective of soft theorem actually allows you to go beyond what the classical derivation gives us, because it suggests further extensions of these results, which so far have no classical derivation. So, throughout this talk I will use the convention that h bar is 1. This of course will be mostly redundant, because we will be talking about classical gravity for most of the talk. I will set velocity of light to 1. So, all units will be measured in terms of c, but I will keep the Newton's constant, at least for most of the talk. So, you will see the Newton's constant explicitly in all the formula. So, let me begin by giving the result, and we will start with a general case, the scattering or collision, because the case of explosion is a special case of scattering, right, because the explosion means that there is only one initial object which explodes into many objects. Scattering is many initial objects going into many final objects. So, let us imagine that there is a scattering in space, and what I mean by scattering is that a set of objects which have 4 momenta, say p1 prime to pm prime, m objects, they come together, they interact, and then they disperse as a set of objects with some different set of 4 momenta, which I will denote by p1 to pn. And these 4 momenta of course satisfy the mass shell condition. So, Pa square, which I have used the metric with 1 minus and rest plus signature. So, Pa square by definition is minus E square, this is the energy, and this is the physical 4 momentum, physical 3 momentum. So, Pa square should be equal to minus Ma square, that is the condition, mass shell condition. Similarly, Pa prime square is minus Ma prime square, and notice that here you are not assuming any relationship between the masses of the initial and the final states. So, during this collision they can exchange mass, they can exchange everything, we make no assumption about what happens during the collision. So, what we will do is we will choose the origin of space time to be in the region where the scattering event takes place. So, a set of objects come together, scatter and then go out. So, the scattering events is localized in space as well as in time, and we will choose the origin of space time somewhere in that region, where exactly it will not matter. And now suppose you have a detector D that is placed at a far away point, which I will denote by x, and suppose it detects this gravitational waveform h mu nu, which I have already introduced earlier. This signal will reach the detector at some time t naught, which is given here. So, t naught is given by r plus correction, r because gravity wave of course travels at the speed of light, right. So, to travel a distance r is just mod x, So, travel a distance r, it requires a time r, but there are corrections because the gravitational drag on the gravitational radiation, because gravity wave is not propagating in flat space time, it is propagating in the background of all the other objects which are around. So, it will have some logarithmic correction to r, and that is what gives the time of arrival of the gravitational wave signal. So, t naught we can take as the time at which the peak of the gravitational wave signal arrives at the detector. So, we have the detector. So, the time refers to the time of the detector. Okay. So, we will define what is called the retarded time, okay, that is t minus t naught. Okay. So, this means that the gravitational wave signal peaks at u equal to 0. Okay. That is where the main part of the gravitational wave signal comes. Okay. But what we will focus on will be on the late and early time tail of the radiation. Okay. Namely, the value of h mu nu at a detector at large positive u and large negative u. Okay. And the reason is that this is the range, this is the region in which soft theorem can have some say. Okay. Soft theorem can give us information about the form of h mu nu at large positive u and large negative u. Okay. So, I have given the results here, but let me just introduce this definition. So, we will define E mu nu, okay, as what is called the trace reversed form of the metric. Okay. So, E mu nu by definition is h mu nu minus half of trace of h times eta mu nu, okay, and you can invert this relation. So, h mu nu has a similar relation by which you can express h mu nu in terms of E mu nu. Okay. So, the reason that I have introduced E mu nu is because the various formulae that I will give take simpler form in terms of for E mu nu, okay, but given the form of E mu nu, of course, you can always work out what h mu nu is from this. Okay. So, you are not really losing any information by working with E mu nu. Okay. And here is the result. Okay. What we will find is that up to gauge transformation, which means general coordinate transformation here, okay, and corrections of order r to the minus 2, okay, which we will not worry about. Okay. E mu nu has the following form for large positive u and large negative u. Okay. So, for large positive u, okay, it has a constant piece and then there is a tail piece 1 over u times b mu nu, and then there is a term of corrections of order u to the minus 2, and for large negative u it has a tail piece and of order u to the minus 2. Okay. And the main point that I will try to emphasize is that this a mu nu, b mu nu and c mu nu, these coefficients, okay, are given solely by the momenta of the ingoing and the outgoing objects, okay, and this does not require any knowledge of the details of the scattering process. Okay. So, it could be a supernova, it could be a binary black hole merger, it could be collision, okay. It does not matter what it is, as long as you know the initial momenta and the final momenta of the objects, of the various objects which come in and go out, okay, you can determine a mu nu, b mu nu and c mu nu, okay, and I will give the formula for these in the next slide. Now, one point to note is that there is a constant piece in E mu nu, okay, but that is chosen by convention, okay, because our convention is that initially, okay, the metric was just eta mu nu. So, h mu nu should have been 0 at u goes to minus infinity. So, the fact that the constant piece has been set equal to 0 here, okay, is a gauge choice. Okay. By a coordinate transformation you can make the constant piece non-zero. But once you have chosen the constant piece to be 0 here, then this is no longer a gauge choice, this is a physical constant. Okay. And we will see the various significance of these in a few minutes. So, here are the expressions for these coefficients that I wrote down. Okay. So, a mu nu, b mu nu and c mu nu are given here. I think all the quantities here I have already introduced. Okay. These are the incoming momenta, these are the outgoing momenta. This vector n, okay, is a 4 vector whose first component is 1, and the spatial components are just the direction cosines of the detector relative to where the scattering took place. So, these formulae are complicated, okay, and we will not need to really look at the details of the formulae, okay. But the main point again is that these involve only the initial and the final momenta and nothing else. No details of the scattering process is necessary for these expressions for A, B and C. Okay. So, here is the formula again. Okay, the formula for E mu nu. So, this A mu nu is what is known as the gravitational memory. Okay. It is called gravitational memory because what it does, what it represents, okay, is a permanent change in the state of the detector after the passage of the gravitational wave. You see, we start with a flat metric g mu nu equal to eta mu nu we have some interferometer, okay, which is placed, which is part of the gravitational wave detector. The gravity wave passes, okay, there is oscillation in the detector, okay, but at the end of the process, okay, the interferometer does not return to its original position. Okay. The distances between the arm lengths of the interferometer gets a permanent shift, okay, that is caused by this mu nu, and this is what is called a memory effect. This is something which has not been observed so far, but one expects that the future gravitational wave detectors will eventually observe the memory effect from various sources. So, this is what is connected to the leading soft graviton theorem, okay, and I will discuss this connection later. These coefficients B mu nu and C mu nu are what can be called the tail terms, okay, because this tells us how exactly it reaches this mu nu in the far past, far future, and how it differs from 0 in the far past. Okay. And these are connected to what we call logarithmic terms in the subleading soft graviton theorem. Okay. And again I will explain this later in this talk. Are there any questions on this so far? So, let me just say a few words about these results. Okay. So, the first point I want to emphasize is that this result is a statement in classical gravity, okay, classical gravity in 4 dimensions, okay, even though as we will see it was originally suggested by quantum soft graviton theorem. Okay. In fact, quantum soft graviton theorem in larger than 4 dimensions. Okay. Nevertheless, we now have a fully classical derivation. Okay. We do not need quantum soft graviton theorem to actually derive this result. We have a fully classical derivation, and I will describe this, at least the logic of this classical derivation later in the talk. Second point I have already emphasized before, that these coefficients A mu nu, B mu nu and C mu nu, these can be expressed in terms of the momenta of the incoming and outgoing objects without knowing what forces operated and how the objects moved during the scattering. And this is a consequence of soft graviton theorem. So, the third point is a technical point. You see in this you have a sum over all outgoing momenta, right, or outgoing momenta as well as incoming momenta. Now, if it so happens that a significant fraction of the energy is carried away by the radiation, by the gravitational radiation, then the sum over A and B should also include integration over outgoing flux of radiation, okay, because you can think of this outgoing flux of radiation also as a flux of massless particles. Okay. So, you think of as a collision process that produces not only massive objects, but also massless particles in the form of gravitational waves, and they will also contribute to this sum. Now, since these results are initially derived or derived in quotes from quantum soft graviton theorem, okay, it had to be tested against various known results, and indeed the result matches explicit known results in special cases. Okay. The result that it was tested first is against an old calculation by Peters, who calculated the scattering of a particle of the Schwarzschild black hole and calculated the gravitational radiation that is emitted during that process. Okay. Again, by examining that at late and early time, we can find agreement with this formula that I showed you. Okay. Then more recently there are papers by these authors where they consider a completely different situation, where you have 2 ultra high energy particles passing through each other, and they calculated gravitational radiation from that process, and again this formula in appropriate limit agrees with what they found. Okay. So, certainly this result matches explicit results in known cases. This point I have already alluded to before, that explosion can be regarded as a special case of scattering when the initial state has just one object. Okay. So, you do not need a separate formula for explosion. Okay. If you examine the formula that I wrote down here, this complicated formula, and set m equal to 1 for example, okay, we can easily see that C mu nu will vanish, because this sum requires m at least 2, because you have to sum over A and B with B not equal to A. So, for m equal to 1, C mu nu is 0, and A mu nu and B mu nu takes their own form. Okay. I have given here the formula for B mu nu in that particular case. Okay. Here the I think there is a this sum, for example, is only over one particle, not multiple particles. Now, this I think is the most surprising result of this calculation, okay. Namely that the contribution to B mu nu vanishes unless there are at least two massive objects in the final state. Okay. This we have no physical understanding of why this happens, okay, even though it is physically significant. Okay. So, the point is that if you take this formula, okay, and assume that the final state has at most one massive object, okay, then you see in this sum, okay, because this includes the product P A square P B square, okay, this will be 0, right, because if there is only at most one massive object, then both P A square and P B square cannot be non-zero. So, this is 0, similarly this is 0, okay, and then the formula simplifies, and then what one finds is that these two terms cancel. Okay. So, if there are, unless there are at least two massive objects in the final state, this B mu nu vanishes. And the reason that this is significant, okay, is because this implies that the coefficient of the 1 over u tail vanishes for binary black hole merger. Because here the final state contains only one massive object, that is the remnant black hole. So, binary black hole merger means that you have two black holes which merge, produces a single black hole and gravitational radiation. Okay. So, the final state has only one massive object, that is the remnant black hole, everything else is massless. In this case, this vanishes. Okay. Now, I have a strong suspicion that this is not accidental, right. There must be something about gravity that we do not understand, okay, that maybe some additional symmetry or something, okay, which is responsible for this vanishing. But right now all we have is this explicit calculation, and we find that B mu nu is 0 in this particular case. In contrast, this coefficient will be non-zero for supernova explosion or binary neutron star merger, and or for collisions like bullet cluster, because in all of these processes, okay, the final state, either the initial state has more than one object, one massive object, or the final state has more than one massive object. Okay. Supernova explosion, for example, a star blows up into many massive fragments. Okay. So, this is what I have already said, that this is the expression for B mu nu, okay, and the fact that B mu nu vanishes for less than or equal to one massive objects in the final state seems to be accidental from this point of view, okay, because it is a result of cancellation between these two terms, and in fact these two terms have very different origin in the calculation. Okay. One of these terms is what we can call the ultraviolet effect, okay, that is this term can be called the ultraviolet effect, and the second term in blue is an infrared effect. Okay. Nevertheless, somehow the ultraviolet and infrared effects cancel each other and give a vanishing result. Okay. And clearly a deeper understanding of this will be useful given its implication for the binary black hole merger problem. Okay. And this will sooner or later be tested, because I think the binary black hole merger has been studied in detail, and once you start discovering the memory effect, we will also start seeing or the absence of this 1 over u tail. Okay. So, this finishes the summary part of the talk. Okay. So, now I will give first the classical derivation. Okay. I will sketch how we derive this result classically. This is, as I said, this is not historically the way it was derived, okay, but I will first give the classical derivation because that is concrete, that is explicit, okay, and then I will describe how we had arrived at this result from soft theorem, because that will give us further insight into extensions of these results. Okay. So, what is the goal? Okay. So, the goal is to find H mu nu or equivalently E mu nu that is generated during the collision process. So, to do this, okay, what we will do is to analyze not E mu nu directly, but its Fourier transform. Okay. Fourier transform in only the time variable. Okay. So, we define E tilde mu nu omega x as the Fourier transform of E mu nu. Okay. And it is a simple exercise in Fourier transform to show that these statements that we have made here, that E mu nu for large positive u has this structure and E mu nu for large negative u has this structure, okay, translates to some singular behavior of E tilde mu nu, its Fourier transform for small omega. Okay, omega is the Fourier the frequency that is dual to t under Fourier transform. So, in particular this constant shift that we have from 0 at u goes to minus infinity to a mu nu as e goes to plus infinity, okay, that corresponds to a pole in the omega plane. Okay, there is a I omega inverse a mu nu, and these late and early time tails b mu nu and c mu nu correspond to logarithmic terms in the expression for E tilde mu nu, okay, for small omega. So, the strategy then will be to analyze this Fourier transform E tilde mu nu and identify the singular terms in the omega variable to compute a, b and c. So, since it is a classical gravitational problem, we solve Einstein's equation. So, what is the Einstein's equation? Okay, so, this is it. Okay. We have the left hand side is the standard Einstein tensor and the right hand side is the energy momentum tensor. So, Tx mu nu is a matter stress tensor, the stress tensor of everything other than gravity. Now, one thing to notice is that we have written the Einstein's equation in a slightly non-standard fashion by including the square root of minus determinant g on the left hand side. Okay. That basically means that we have an extra factor of square root of minus determinant g included in the expression for the matter stress tensor, because this is a technical point, makes life a little more a bit easier, okay. But we could also do without this, okay. That will just reorganize the analysis in a slightly different way. So, given this equation, okay, we will then write g mu nu as eta mu nu plus 2 h mu nu, this is how we have defined h mu nu, okay, and we will also introduce E mu nu, okay, which is related to h mu nu by this trace reverse form. Okay. And once you have decomposed the metric in this way and defined E mu nu this way, okay, all indices will be further raised and lowered by the flat metric eta, that is the convention we will be using. Okay. So, E upper mu nu is just the lower raising of the indices of E by eta. Okay. And then we will rewrite Einstein's equation in terms of E mu nu, okay, and we will use what is called redundant gauge, this is a particular choice of coordinate system, okay, and that takes this form. This looks simple, this is the Laplacian, standard Laplacian in flat space time, okay, but the simplicity of course is hidden here, okay, because what T mu nu is, okay, there is a sum of Tx mu nu which appears here, okay, and then what we call the gravitational energy momentum tensor, this contains all the nonlinear terms from the left hand side. Okay. So, what we have done here is that we have just kept the linear term in H from the left hand side, that is box E mu nu, this you can easily check, and everything else that is quadratic and higher order in H we have taken to the right hand side and called this Th. Okay. So, even though the equation looks simple, we have not really done anything, right, we have just reorganized the terms in the equation. Okay. So, as we have said, from now on all indices will be raised and lowered by the flat metric eta. So, this is the equation you have to solve, right, box E mu nu equal to minus 8 pi g T mu nu. Now, formally this can be solved by writing E mu nu as minus 8 pi g times the integral of the Green's function convoluted with T mu nu, right, that is what the Green's function does. It solves equations of this kind, right, and we will use retarded Green's function because we are trying to solve an initial value problem, right. Initial conditions are given, final E mu nu is what we want to determine. Okay. But of course, this is somewhat of a cheating, this is not really a solution because the T mu nu on the right hand side includes C mu nu, right, because T mu nu has Th mu nu, okay, and Th mu nu in turn depends on H mu nu and hence E mu nu. So, this is just a formal expression, but this is not solving for E mu nu, right. This is an identity. You can think of this as an identity, but this is not really giving a solution for E mu nu. Nevertheless, this equation is useful, because what you want to do is to study E mu nu not for general x, but a large mod x, right, because you are looking at detectors which are far away. We want to, we do not care about 1 over r square corrections, right, we want to look for the 1 over r piece. Okay. So, we take this expression for E mu nu and take large mod x far away, okay. And then one can show by evaluating this integral using saddle point that E tilde mu nu, the Fourier transform, let me remind you what E tilde mu nu was. E tilde mu nu was the Fourier expansion, Fourier transform of E mu nu. Okay. So, what one can show is that E tilde mu nu is related to the Fourier transform of T mu nu, which are denoted by T hat. So, this T hat is the complete Fourier transform in all variables. Okay. Nevertheless, E tilde mu nu omega x is related to the Fourier transform of T mu nu, the T hat mu nu, by this simple relation. Okay. So, here k, of course, E mu nu depends only on omega. Right. So, k is determined in terms of omega. So, it is given by omega 1 n hat, and n hat is just the unit vector along the spatial direction x. Okay. So, this is an identity. Okay. So, if you want to compute E tilde mu nu at large x, we just have to compute the Fourier transform of T mu nu at the Fourier transform of T mu nu. Okay. That is all you have to do. Okay. And let me remind you again that this T hat mu nu of course contains E, right. So, it is not that we have gotten a solution, right. We have to somehow solve this iteratively, and we will see how we do this. Okay. Are there questions at this point?
Can you clarify, looking at that equation, I see that E tilde mu nu depends on x, but the right hand side you've integrated over x, no? Or am I missing something?
Right hand side meaning here?
Yeah, that's...
No, r is mod x, right?
Okay.
R is mod x and the direction of x is in n hat, right. So, the information about x is there, it is just hidden. Yeah. So, it depends both on the mod x as well as the direction. Okay, so here is the equation again. So, E tilde mu nu is given by T hat mu nu k, okay, and T hat mu nu k is given here. Okay. So, we should, maybe I should have used some other index y, right. I think that is maybe what is confusing, right. Yeah. So, this integral is some integral over y, right, not x is the position of the detector.
Well, yeah, what I was confused about is r is x, that's what I didn't realize.
Yeah, r is mod x, and but not just r, but k also contains x, because k, the spatial component of k, right here, is has the n hat, right, and that also has the has information about x. Okay, so think of this as integral over y, not over x. Okay, x is the detector position. Okay, so now we can, this integral over is over the whole space time region, right. This is the Fourier transform. But what we will do now is to divide the integration region over x into two parts. The first part we call the scattering region. Okay. Remember that we have chosen the origin around x equal to 0. Okay, we can call it maybe y equal to 0, whatever. Right. The origin is at the scattering region is around, the origin is inside the scattering region, right. So, the scattering takes place in a certain space time region, okay. The origin is somewhere inside. Okay. So, this region R is a sufficiently large size region, okay, where the scattering takes place, and then we call the complement of R the asymptotic region. Now, the point of dividing it into these two regions is the following. You see, our goal is to compute terms in T hat mu nu that are singular as omega goes to 0, right, because we have this result, that in order to compute A, B and C, we are looking for terms that are singular as omega goes to 0, omega inverse and log omega, okay. And omega goes to 0 means k goes to 0, right, k is omega times 1 n hat. So, k goes to 0. So, what we are looking for are singular terms as k goes to 0. Right. So, let us set k equal to 0, we get integral d4x d mu nu x. If this integral is over a finite region, say R, then this integral is finite. Okay. There is no possibility of getting a singular contribution from this integral. So, the idea is that because your goal is to compute terms in t hat mu nu that are singular as omega goes to 0, we can ignore the contribution from the finite region R in this integral. On the other hand, in the asymptotic region, at least Tx mu nu can be simplified by thinking of this as due to incoming and outgoing object trajectories, and they are moving under each other's long range gravitational field. Okay. Now, it could also be that if the particles are charged, there is long range electromagnetic field. Okay. I did not write in the formula the electromagnetic corrections, but if there are charged particles, there are electromagnetic corrections which also we can compute. It will just make the formula a little more complicated. Okay. So, let us assume for simplicity that the particles are uncharged. So, the only long range field that acts between them is the gravitational field. Okay. So, the idea is that here in this region, the particle motion is controlled by the long range gravitational field between these particles, between the outgoing and incoming particles, okay. And the integration from this region can be ignored because that is not going to give singular contribution to t hat mu nu. So, here in one slide I have written down the summary of all the equations that we have to deal with. So, the first two lines describe the expression for Tx, right. Tx mu nu, okay. We are thinking of these external objects as particles, okay, but with possible multiple moments. Okay. So, here you see the leading term in the expansion for T mu nu. Okay. This is the standard expression for the energy momentum tensor of particles moving in space time. Okay. Normally, we would have a 1 over square root of minus determinant g multiplying these, but that has gone because of this unusual definition of Tx mu nu, where we include the square root of minus determinant g on the left hand side and the right hand side. Okay. Now, this is of course not the complete expression, okay, because the objects, the external objects are not particles, right, they are structured, they have structure. Okay. So, because of the fact that the external objects have structure, there are corrections to this formula, okay, which you can call the multiple moments. They involve derivatives of the delta function, okay, but those you can show do not contribute to the order that you are working in, because derivatives of the delta function, if we include, right, then in the Fourier transform, when you take the Fourier transform, they will bring down additional parts of k, right, which means additional part of omega, and they are not singular enough. So, that is why we can ignore the derivatives of the delta function and just think of the external objects as particles to this order. Then you have this expression, this equation here, the T mu nu being given by the sum of Tx mu nu and Th mu nu. This is the gravitational energy momentum tensor. Right. Now, I have not written down the expression for the gravitational energy momentum tensor. It is a complicated expression, okay, but it is known, right, because it is after all whatever you have on the left hand side of the Einstein's equation, you bring to the right hand side except the linear term. Okay. So, it is a completely known expression that you can deal with. Then you have this equation which you wrote, box C mu nu is minus 8 pi g T mu nu. This includes the sum of both gravitational and matter energy momentum tensor. And finally, we have the equations that determine the particle trajectories. Right. These are the geodesics along which the particles move. Okay. Gamma here is the Christoffel symbol that is produced by the gravitational fields of all the other particles. So, we also have to put of course boundary conditions, right. We put the boundary condition for the particle trajectories. So, at tau equal to 0, so the convention that we are using is that tau is 0 on the surface for every particle and it increases outwards. Okay. So, tau equal to 0, it is Ra, right, R1, R2, etc. So, that is what we have here. And the other boundary condition we put at tau equal to infinity, because that is where you know what the asymptotic velocities are, because that is just 1 over ma times p mu, right. These are our given data, because you want to express the final result in terms of the p mu's, right. So, this everything then should depend on p mu. Eventually, we will see that the dependence on R mu will drop out. Okay. So, the singularities that we are looking for actually only depend on these data. Okay, but to start with you have to put these asymptotic conditions because it is a second order differential equation and we need two boundary conditions to solve these equations. Okay. So, the idea is that we now solve these equations iteratively, okay, starting with the leading solution, okay, where you take the set the metric to be flat metric E mu nu equal to 0, okay, and we take the particle trajectories to be the free particle trajectories, okay, just constant plus something proportional to tau, right, constant velocity. This is the free particle trajectories and this, so these are for outgoing and these are for incoming. Okay. So, you start with this and then substitute in these equations and try to solve these equations iteratively. Okay. And what we find is that this generates a series expansion in Gm times omega, okay, and possibly with corrections involving log omega factors. Okay. So, this automatically produces an expansion in omega, right, which is what we are looking for, right. We are looking for terms that are singular in omega, right. We want a leading term that is omega inverse and then the logarithmic corrections, okay. And so, because of this it is enough to do just one iteration, okay. After one iteration you can stop. If you want to go beyond, we have to do higher number of iterations. Okay. So, here are the steps that we need to follow. Okay. So, the starting solution has Th mu nu equal to 0 because we start with E mu nu equal to 0. Right. So, E mu nu equal to 0 means H mu nu equal to 0. So, no gravitational energy momentum tensor. So, the starting solution has Th mu nu equal to 0 and the matter energy momentum tensor is given by that of the free particles, okay, because the matter moves on a straight line. So, we just get free particle matter energy momentum tensor. So, that is good. So, this gives the source. Okay. So, you can now compute E mu nu using retarded Green's function, right, because once we have Th equal to 0 and Tx known, we just substitute in the second in this equation, right, and compute E mu nu using retarded Green's function. After you have computed E mu nu, we can use this to compute Th mu nu because Th mu nu depends on H mu nu, right, which is the same as E mu nu up to this trace reversal. So, once you have computed E mu nu from the first step, we compute this, use this to compute matter energy momentum, the gravitational energy momentum tensor. But we also do something else. We use the same gravitational field E mu nu to compute a Christoffel symbol. And using this data, we calculate the Christoffel symbol at the position x mu due to all other objects other than A, right. So, we basically calculate the Christoffel symbol along the particle trajectories due to all other particles. So, using this we can now correct the trajectories of the particles, right. X mu of tau was the trajectory that we started with, that is the free particle trajectory along straight line. Now, because of the Christoffel symbol, the particle trajectories get corrected, right. So, we correct the particle trajectories and then we use these corrected trajectories to compute corrected Tx. So, this completes the first iteration, okay. And as I said, we can stop after first iteration if we want the terms that we want, that we mentioned, that namely omega inverse and log omega term. Okay. So, at this stage you have the first order correction of Tx mu nu because you have corrected the particle trajectories and use that to compute Tx, okay. And you have the first order correction to Th mu nu because we use the first order correction to E mu nu to compute Th. Okay. So, then the final step is that we compute Tx plus Th and take its Fourier transform, okay, and that gives you E tilde mu nu, right. That is what we are looking for. So, this is the result that we get at the end. Okay. Now, I will not describe details of the calculation. Okay. It turns out that because you are trying to iterate the Green's function, okay, effectively you can organize this into a Feynman diagram like expansion. Okay. The only difference is that the vertices are slightly different from what you will get in quantum gravity and the propagators are somewhat different. Okay. For example, for the gravitons we have to use retarded propagator instead of Feynman propagator, okay. But otherwise the organization of these terms is just like a Feynman diagram calculation, one loop Feynman diagram calculation. So, you do that calculation, okay, and extract the logarithmic pieces, and this is what you get. At the end of the long calculation, this is what we find as the answer. Okay. And now here, okay, if you substitute k equal to omega n, right, and then take the Fourier transform in omega, we get the result for E mu nu that we had given in the beginning of the talk. Okay. That produces the A mu nu, B mu nu, and C mu nu. So, this is a purely classical derivation of the results that we are looking for, okay, the results that I mentioned at the beginning. Okay. No quantum gravity yet, right, but I will explain what it has to do with quantum gravity, how we initially arrived at this result using quantum gravity. But before I go on to that, let me just say a few words about the physical origin of the various parts of B mu nu and C mu nu, okay. Because as I said, there are the B mu nu has two terms, two kinds of terms, right. This we call the ultraviolet, this we call the infrared, and the cancellation that I mentioned for say binary black hole merger is a cancellation between these two terms, right. So, let me now try to explain the physical origin of these two terms, so that it is clear that they seem to have different origins. So, first I will start with this term, right, the origin of this term. So, as we discussed earlier, the memory effect produces a jump in H mu nu, that is a constant piece, right, the A mu nu piece. Okay. So, the memory effect produces a jump in H mu nu. So, you can think of this as a step function in the expression for H mu nu. Okay. So, there is a piece of gravitational wave that is like a step function, okay, which is a Fourier transform 1 over omega. But what happens is that this gravitational wave that is associated with the memory effect, okay, this of course does not reach the detector at one go, right. This has to travel in the background of all other particles, right. This has to climb the gravitational potential of the other particles and reach the detector. Okay. And it turns out that what happens is that during this propagation, okay, the propagation of the gravitational wave associated with the memory effect in the background geometry of the hard particles, okay, this propagation disperses the gravitational wave form associated with the memory effect. Okay. So, instead of being a step function, okay, it gets a tail, okay, and that the effect in Fourier space is to multiply the omega inverse term, that is the memory term, by a phase factor of this kind. Okay. And if we expand this in powers of omega, okay, the omega inverse gets cancelled by omega and you get a log omega, and that is proportional to this term. Okay. So, this is the origin of the second term in the expression for B. This term comes from that origin, and we call this infrared because you see that the effect is coming from the range between omega inverse and r, right. Log omega r clearly indicates where it is coming from, it is in the range between omega inverse and r is the detector distance, that is a very large distance, that is infrared. Now, the origin of the first term in the expression for B. So, this term arises from the following source, that after the scattering, imagine that a set of objects have come together, scattered and gone out. Okay. After they have gone out, okay, they still exert long range gravitational force on each other, right. And because of this long range gravitational force on the particles among themselves, they continue to accelerate or decelerate. Okay. So, because of this continued acceleration, because of the long range gravitational force between the final state particles, the radiation does not stop, they continue to radiate. Okay. And it is this effect that leads to the first term in B mu nu, okay, and that is proportional to this. Okay. This effect we call infrared because the dominant contribution comes from in between the scattering region, that is L and omega inverse, right. That is the range of momentum that contributes to this term in the expression for B mu nu. Okay. But nevertheless, as I said, this term cancels the infrared term for the special case of binary black hole merger. Okay. and the contribution to c mu nu comes entirely from the early acceleration of incoming particles. So, that is the analog of this term, okay, due to long range gravitational force. Okay. So, that is in fact easier to understand where that effect is coming from. Okay. So, this is more or less the classical derivation of the results that I quoted. So, are there any questions at this point? Okay, so let me now go to soft graviton theorem, okay, and I will call this the heuristic derivation of from soft graviton theorem, because as we will see that the derivation is not a rigorous derivation, okay, it requires some guesswork. Okay, so, this is what I will do. It is a combination of logic plus guesswork plus test, okay, against various known formula. Okay. Here I will use the notation h bar equal to 1, c equal to 1, and also I will set the Newton's constant to 1 over 8 pi, okay, but at the end I will restore the Newton's constant, okay, but in the intermediate stage I will just set this equal to 1 over 8 pi. And here are various earlier references on the soft graviton theorem. But before I describe the derivation, okay, or the so called derivation of the soft graviton based on soft graviton theorem, okay, let me give a motivation for why we want to do this. Because after all, I have already said that the analysis based on soft graviton theorem will involve some guesswork. Okay. But given that we already have a direct classical derivation, right, you may ask why should we now go back to study soft graviton theorem. Right. Maybe historically this is how it was derived first, but now that we have a classical derivation, I mean, why not just stick to the classical derivation? The point here is that higher order soft graviton theorem can be used to derive higher order results for the gravitational waveform, and we will describe some higher order results in the gravitational waveform exactly in the same spirit that we described earlier. And for these we do not yet have a classical derivation. Okay. So, certainly soft graviton theorem is a simpler way of arriving at the results, right, even though we are not sure if the results are correct because it is not a rigorous derivation. Okay. Nevertheless, if it gives a result that is correct and that has been tested, right, maybe that gives a confidence that we can even trust the next order result, right. At least we can use the next order result to arrive at some conjecture which we may now try to prove using classical methods. Okay. So, that is where the value of the soft graviton theorem lies. And this is why soft graviton theorem is still a useful source of new conjectures for classical gravitational waveform. So, let me now describe briefly what soft graviton theorem is and what is the logic that we use to get to the results. So, what is soft graviton theorem? So, let us suppose that we have a general coordinate invariant quantum theory of gravity coupled to matter fields. And in this theory, we consider an S matrix that involves some arbitrary number, say n, of external particles of finite momentum p1 to pn. These particles can be anything. Okay. They can be gravitons or photons, they can be heavy string states, okay. They can be nuclei, atoms, molecules, okay. Even stars, black holes, okay. It does not matter, okay. Any external particles. And we have m external gravitons carrying small momentum, which I will denote by k1 to km. So, what soft graviton theorem gives us is an expansion of this amplitude in a power series in k1 to km in terms of the amplitude without the soft graviton. In other words, soft graviton theorem is a formula, okay, which tells us that knowing this scattering matrix, just n point scattering matrix of finite momentum p1 to pn, we can actually write down a formula for a scattering matrix that involves the same external particles of finite momentum and m external particles carrying small momentum. And the way the formula is presented is that there is an expansion in powers of k of the soft momenta, and soft graviton theorem determines the coefficients of expansion to certain order that I will describe. Okay. That is the content of the soft graviton theorem. So, this theorem can be proven in general with some assumptions, okay, and this includes string and M theory. Any theory of quantum gravity, any consistent theory of quantum gravity has soft graviton theorem, with some assumptions, and I will describe in the next slide what the assumptions are. So, the first assumption is that the scattering is described by general coordinate invariant one particle irreducible effective action. Right? This is in short form, we also call it the effective action. General coordinate invariant effective action should describe the scattering. This basically means that a gravitational theory should have no anomaly. Right? It should be diffeomorphism invariant, and this of course is expected of any theory of quantum gravity, any consistent theory of quantum gravity. And if we have such a one particle irreducible effective action, then T amplitudes computed from this will give the full quantum results. We do not need to know the explicit form of this 1 pi effective action, the existence is enough to prove soft graviton theorem. The second assumption, which is more subtle, is that the vortices of this 1 pi effective action, right, say n point vortex that you compute from this 1 pi effective action, they should not contribute powers of soft momentum in the denominator. Now, in normal action, right, local action, the vortices are always polynomial momentum, right. So, you do not expect that vortices will have 1 over momentum, but here you are talking about the effective action, right, where you have integrated out the loops, and loops include massless particles. So, because of this assumption is not always true, and indeed it breaks down in d equal to 4 precisely because of the infrared divergences. So, soft graviton theorem as stated does not work in d equal to 4. So, let us begin at d larger than 4, and see what soft graviton theorem gives us, and then we will see how to come down to d equal to 4. So, here is the result for soft graviton theorem, or the structure of the results. So, let us suppose that gamma is the scattering amplitude of any set of finite energy or hard particles. The finite energy particles are what we call hard particles. Those are the particles carrying momentum p on to pn. So, what soft graviton theorem tells us is that the scattering amplitude of the same set of states with m additional soft gravitons of polarizations epsilon and momentum k. So, you have, let us suppose that you have m soft gravitons which has polarizations epsilon on to epsilon m and k1 to km momentum, then this scattering amplitude is given in terms of gamma by a formula like this. And this formula is known to be valid up to sub-subleading order in expansion in powers of soft momentum, that means leading, subleading and sub-subleading. So, what is S? S is an operator, it is a known universal operator, and what we mean by operator is that it involves derivatives with respect to the moment of the hard particles. So, the gamma is a function of the moment of the hard particles, right. So, S includes in particular derivatives with respect to the momenta, and also there are matrices acting on the polarization of the hard particles. The hard particles may have a photon, for example, right, or a massive spin particle carrying spin. So, this includes in general matrices which act on the polarizations, right, which acts on the polarization of the photons, hard massive spin particles and so on. So, that is the kind of operator we have here, but the important point is that this operator is universal, irrespective of what gamma is. It can be any complicated theory that produces this hard particle scattering matrix, which may be complicated, but this operator is universal. You do not need to know anything about the theory to find what this operator is. This is universal up to subleading order. At the sub-subleading order, there is a non-universal piece to this operator. So, now, this is quantum, right. This is a result purely in quantum gravity theory, quantum gravity in higher than 4 dimensions. Now, in this one slide, I have described how to take the classical limit of this quantum result. So, what we mean by classical limit? So, classical limit here will correspond to the limit in which the energy of each hard particle becomes large. So, classical limit means that we are no longer scattering photons or gravitons or molecules or nuclei, but you are scattering large objects, okay, whose masses are large compared to m Planck, okay, maybe very, very heavy string states, okay, or more normally if you want to make connections with nature, stars and black holes. Okay, they have masses much larger than m Planck. Okay, so those are the objects that we are scattering. Okay. So these will be represented by wave packets which have sharply peak distribution of position, momentum, etc., position, momentum, spin, etc., right. So these are now no longer ill defined, both position and momentum can be defined to very good accuracy. So what one finds is that in this limit the soft factor becomes a multiplicative factor instead of a differential operator, because after all I said that this involves derivative with respect to momenta, right. But if the wave function is highly peaked in the position space, then derivative with respect to momentum can be replaced by the position x mu, right, because after all del p mu is proportional to x mu, right, up to factors of I. Okay. So that is the way we convert this differential operator into a multiplicative factor. Okay. Furthermore, one finds that this multiplicative factor now becomes a product of factors, one for each soft particle, right. So instead of being a complicated function of all the epsilons and all the k's together, now you have product of each soft particle individually, okay, and there is a single factor S which depends on one polarization and one momentum. So given this structure, okay, now you can ask what is the probability of producing m soft gravitons with given quantum numbers epsilon k. So if there are m identical soft gravitons, then we have m identical factors S epsilon k in this product. Okay. So that gives you S epsilon k to the power m. Okay. Now this is the amplitude. So to calculate the probability you have to take the mod square of the amplitude. So S epsilon k mod to the power 2m. Okay. Then because you are talking about identical external particles, you have to include a symmetry factor, that is m factorial. And then there are some phase space factors which I have not written down. So this gives you the probability of producing m soft gravitons with a given quantum number epsilon k. Now we can ask what is the distribution of this in the space of m, and you can easily convince yourself that in the soft limit, in fact in the classical limit, this is a very large number, S epsilon k becomes a very large number. And because of this is sharply peaked in the m space, okay, and the peak is around this m equal to mod epsilon mod s square times some phase space factor, right, which I have not written down here. So this is what we can call m classical k, right. So from the soft graviton theorem we get a classical formula, because even though the quantum theory allows emission of photons of arbitrary numbers, right, you can have 1 photon emission, 2 photon emission and so on, but the probability distribution is peaked around some particular number of photons, right, that is m classical. So once you have gotten m classical, that tells you how many gravitons are produced in each bin. For every epsilon k, how many gravitons are produced. Okay. And this can be related now to flux of classical soft radiation, okay, because we no longer have a distribution, we have a sharply peaked distribution. Okay. And from this we can work out the classical gravitational waveform, because gravitational waveform is classical soft radiation flux is just the mod square of the gravitational waveform, right, up to a phase, right. So this allows us to determine the gravitational waveform up to a phase, okay. And that is what we call the classical soft theorem, okay, that starting from this quantum formula and taking the classical limit, we can determine the classical gravitational waveform that is produced during a scattering process. And here is the formula. I have translated to E or E tilde. It is omega we have already introduced, omega is the Fourier transform, okay, the energy. R we have already introduced. Okay. This eta A is just a symbol, it is 1 for outgoing and -1 for incoming. I just did not want to write a long formula with both outgoing and incoming particles, so I just wrote it in one line, okay, but it is 1 for outgoing, -1 for incoming. Okay. Sum over A runs over all the hard particles, okay, the particles which are scattering. Okay. N I think I have introduced here, the same N. Okay. so the only thing I need is J, right. You see the J is defined here. So, let me explain what J is. So, J is the angular momentum of the particle, of the eighth particle. Okay. So, suppose in the far past or far future the object has a trajectory of this form, okay, a constant plus a constant velocity. Okay. Then J is given by this is the orbital part, orbital angular momentum, and then there is a spin part. Each particle may be spinning around its own axis. So, that part you have to add. Okay. This will not play a major role in what we are going to say, okay, but J is given by this. Okay. And now, if we substitute this expression for x, okay, we see that the term that is linear in tau cancels because it is antisymmetric in mu nu, okay, and what we are left with is a finite contribution. Right. So, this then says that knowing the final particle trajectories and the initial particle trajectories and the spins of the final and initial particles, we can work out what the gravitational waveform should be. That is the content of the soft graviton theorem in d dimensions, but d has to be larger than 4. Are there any questions on this? Pardon? Oh, there is a party, okay. Okay, so can I proceed? Is it okay so far? Okay. So, this is soft graviton theorem in d dimensions. But now we come to d equal to 4 because that is what we are interested in. So, in d equal to 4, if you start with the quantum soft graviton theorem, there is already a problem. Okay. There is already a problem because S matrix does not really make sense. Right. Quantum soft graviton theorem is a statement on S matrix. Right. It relates the S matrix with a finite number of soft particles with S matrix without those soft particles. Okay. But the S matrix itself does not make sense in 4 dimensions, it is infrared divergent. Right. So, it makes, if the individual pieces do not make sense, then that makes the soft factor itself ill defined. Okay. So, let us forget the quantum root, okay. But let us say that let us take the classical root. Okay. After all, we have a formula here. Okay. So, why not set d equal to 4, okay, and try to get the classical soft theorem from there. Okay. So, that is what we attempted first. So, naive guess will be the classical waveform is still given by the same formula that is given here, okay, except that I have set d equal to 4. In this previous formula, if I say d equal to 4, this is what I get. But now there is a problem, and that in fact is because of the infrared divergences, although you do not see that kind of link directly. So, the problem is that because of the long range force that acts on the initial and the final trajectories, the trajectory of the 8th particle has a logarithmic correction. This is in fact a simple exercise, right. You can check that if you have a Coulomb potential, is a 1 over r potential, and you have a particle trajectory that is going radially out, okay, then that particle trajectory has of course a linear piece, that is a constant velocity piece, but then there is a logarithmic correction. So, if you use this particle trajectory, okay, and compute j, okay, you see that it is ill defined because now there is a log tau piece. Right. Earlier the linear part of course cancels because of the antisymmetry, but this part does not. Right. So, you are left with something that is proportional to log tau. Okay. So, what do you do with this, right, because now the tau goes to infinity limit does not make sense. So, that is the reflection of the infrared divergence, but in the classical formula. So, then we have to make a guess, right. So, the guess that we made is that large tau A divergence is somehow cut off by omega inverse. Okay. So, the prescription that we gave to regulate this, okay, is simply that we replace tau A by omega inverse in this formula, okay, and get a formula for j mu nu that is regular, but it has a logarithmic dependence on omega. Okay. So, that is the guesswork. I said that it involves some guesswork. This is the part that requires a guesswork, okay, that when you cannot make sense of the formula, you regulate it in a way which looks sensible because omega is the only dimension, full quantity that you have, right. Just by dimensional analysis, tau should have dimension of inverse energy, and that is the only natural quantity we have as a regulator. So, these BMUs of course can be calculated explicitly because this depends on the long range forces. right. The logarithmic correction depends on a long range force between the particles. So, you can compute the B's, and now you have a complete expression for J that you can substitute in this formula and try to get a soft formula for E tilde. And this is what you get. So, this part of the formula is exactly what we showed you. This part is something that is put in extra. This is a phase, right. Remember I told you that E tilde is determined only up to a phase. Okay. So, this phase we have to compute independently, right, and put it in. And I was mentioning that two kinds of terms, right, which cancel in the expression for B mu nu. So, in this language it is a cancellation between this phase term and the rest of the soft factor that is responsible for the cancellation between the two terms in B. Anyway, so the point is that this gives the desired result, right. This formula for E tilde mu nu, okay, is exactly what we had earlier. Okay. That is a rewriting of what we had earlier. Okay. And this is the way we had first derived soft theorem for the classical soft theorem or the asymptotic form for the gravitational radiation. Okay. And as I said, later on we went and did the classical computation directly and checked that this formula is indeed correct. Okay. So, I am now almost near the end. So, let me say a few more words. Given the success, we can perhaps attempt to arrive at new conjectures using subleading soft graviton theorem, because I told you that the soft theorem for gravity is known up to subleading order, right. We have only used up to subleading order, right. Omega inverse is the leading term, log omega is the subleading term, right. Why not go to next order? So, the subleading order soft graviton theorem is known. It is non-universal. There is a part which is non-universal, okay. But you see the logarithmic correction that we had came from J, right. And the part that involves J, part of the soft theorem that involves J is universal, that does not depend on a theory, right. The non-universal piece is something that is insensitive to J, to the angular momentum, the orbital part of the angular momentum. Okay. So, given this, okay, we just went ahead and computed the next order correction, okay, made a guess by using the same logic. We made a guess for the next order correction to gravitational waveform, right. What does subleading soft theorem tell us about the next order correction? Okay. So, what one finds that this, if you trust this, if you trust the next order term in the soft theorem, then this leads to a definite prediction for terms of order omega log omega square in the expression for E tilde mu nu. And if you go back to the U space, the retarded time coordinate, then this translates to terms of order log mod u over U square. Remember that earlier the leading term was A mu nu, the constant piece, that is the memory. Then there is 1 over U, that is the first tail, this is the next order tail, log mod u over U square. And here is the expression. So, this is the correction. So, as u goes to infinity, we have u to the minus 2 log mod u times f mu nu, this is a constant which is given here, and then as u goes to minus infinity, you have u to the minus 2 log mod u times g mu nu, where g mu nu is a constant that is given here. Okay. Again, the important point here is that these f mu nu and g mu nu are determined completely in terms of the same data, incoming momentum and outgoing momentum, right. You do not need anything else. This formula is a purely classical formula, this is a prediction for classical radiation, but this has not been tested using classical techniques, right. In principle it is testable, you just have to do the iteration one more time and see if we get this result, right. But so far the only derivation or only quote unquote derivation of this formula is through soft theorem. Okay. So, this is what the reason why soft theorem is still useful, even though it is a purely classical result, it can be derived in principle purely classically, but soft theorem lets you get to the result much quicker than the classical analysis. Okay, so, I am on to my last slide, okay, some future directions. Okay. So, if we look at the expression for this E tilde. A general statement is that if you have polynomials in omega, in small omega expansion, then they typically lead to delta function and the derivatives in the u variable, right. The Fourier transform 1 is delta u, right. Fourier transform omega is delta prime u, omega square is delta double prime u, and so on. So these terms are all localized around u equal to 0. So if you are looking for power law decay in u, then these should come from non-analytic functions of omega in the frequency space. Okay. So what you are looking for in these tails, okay, even higher powers of 1 over u, are non-analytic terms in omega in the frequency space, and one expects that the non-analytic terms in frequency space will arise from infradivergent terms and therefore should be determined by soft physics, okay, because infradivergence is controlled by the soft physics. So here are the two questions that we would want to answer, okay, and I think it may be possible to answer this. The first is, can we develop a systematic procedure for computing all higher order terms in the large U expansion? Right. We gave constant piece 1 over u and you have a conjecture for this log u over u square, but can we generate a whole series? Can we have a systematic procedure for generating the whole series of this 1 over u expansion? If we can do this, then the next question that we would want to ask is, do all such terms vanish for the binary black hole merger problem? I forgot to mention that if you look at this complicated formula and apply it to binary black hole merger, again the result vanishes. Okay. There is no signal of log u over u square in the binary black hole merger. Okay. Again, we do not understand why this is so, but that is the result of this complicated formula. Okay. So this is a question certainly that is worth exploring, right, because this is certainly something that is going to be testable in the near future. So I think I will stop here. Thank you.
So any questions? Yeah.
That's better. So it's very interesting that a lot of the results seem to be independent of what the theory of quantum gravity is, other than it reduces to Einstein's theory in the appropriate regime. Are there any things along these lines which would distinguish between different theories of quantum gravity? In other words, things we could look for in gravitational waves, or are gravitational wave phenomena sort of going to be insensitive to which theory it is?
Yeah. So the point is, if you look at the gravitation, the subleading soft graviton theorem, right, I said there is a non-universal piece. That piece does depend on the theory of quantum gravity. The different theories of quantum gravity will give different results for the non-universal piece. But I think to see it in a direct experiment will be very hard, because we expect the quantum gravity corrections to be 1 over m Planck suppressed, right. I think that will be very hard to see. I mean, what the part of the non-universal piece that it will see, that experiments will see, is that different objects have different structure, right, and that is why their subleading corrections will differ. Okay. That different structure of course will also include the fact that different quantum gravity theories will have different local interactions, but that will be very, very small, I think. So I doubt that gravitational wave experiments will actually be able to distinguish different quantum gravity theories.
Other questions? Huh?
Did this vanishing for the binary black hole merger problem depend on a very detailed way on the dimension?
They are all in 4 dimensions.
Yeah, you don't expect anything like this to hold in any other dimension?
No, probably not, because if we look at the higher dimensions, this is the correction, the logarithmic terms cancel. So if you look at the d-dimensional formula, right, here you do not have such simple structure. This is a d-dimensional formula. So it is only in 4 dimensions that this vanishing seems to take place.
Any final questions here?
So I understand that the amplitudes people can compute gravitational waveforms from their amplitude. Do you know if they can reproduce these results?
So far they cannot, because they are looking at the early time this in-spiral problem, right. So that's the regime that they do this computation. So at least so far their calculations doesn't reproduce this, but I have been told that I mean sooner or later they will start seeing the effect of these tails in the calculation.
Anybody else? If not, then thank you very much again.
Thank you.
Yes, I'm just going to say a few words. I know it's been a long workshop, but I think very successful. I learned so much, and we covered so much ground, all the way from M theory and supergravity, brains, dualities, gauge theories, gerbs, cohomotopy, and sorry about the music. They usually are late in this, but I think they might be celebrating with us the close of a successful workshop. So this is a third, let me talk about a little bit of logistics. As I mentioned to most of you, we're going to post the videos on the website, and also if we can get your transparencies or notes, if that's okay, I'll send an email about that. And so this is a third conference in a series. Well, it wasn't a series. It was one in Durham, one in Singapore, and this is a third. 3 is a series, I hope. But now we know there's a 4th in Singapore, to which we look forward. So perhaps we could try to standardize this into an actual series. So perhaps we can make the name uniform. It's been a different name every time, so it might help it look like a series if we have the same name. So, so perhaps we could make it as general as possible. There's this string math, and in coming up with this name, Urs and I thought that M theory in mathematics is a wide enough title. Does that make sense? Should we? What do you think, Mang? Because you're organizing the next one. It'll give it some.
I'm not sure if I can change the name with the people. I'll try.
Oh, you already set the name?
Yeah,
Oh.
that's equal to the first one. So the new geometry of the 21st century, like it's part 2.
Oh, part 2. I see.
So I'll ask.
So alternative could be we could do M theory mathematics and then a secondary title. Make. I mean, we all here know that these are series, but for the external observer, it doesn't look like it is unless we put an effort into making it look like a series. Yes. Yeah, so I think that's all what I wanted to say, and I appreciate all of you coming here, and it was wonderful seeing all of you, and thank you so much for your contributions, and safe trips back home, and I hope to see you soon back here, and also next time in Singapore. Okay, thank you so much.